in advanced, we have started to look at changing our variables with this kind of formula here. Okay, so this is using that same concept, but with lots of other types of equations. So I'll read through the blurb that it says there. It says, in real problems, we come across some situations in which it is not easy to measure directly the rate of change of the quantity that we wish to investigate, but it may be relatively easy to measure the rate of change of some other quantity. Problems with related rates arise when there is a function that relates two variables, such as x and y, where both variables are also functions of another variable, such as time, kind of like our parametric equations, for example, a third variable in there. So we've seen this formula before, related rates of change. If y is related to x is related to t, then the instantaneous rate of change of y with respect to t uses the chain rule. Bit of a wordy explanation there. So our chain rule, dy over dt equals dy over dx times by dx over dt. Just remember, we will be changing all of those variables that are in these equations, but it's always important to get the cross-cancelling happening to get the dy over dt or whatever it is, the rate that you want. Okay? All right.
Why does it matter which letters you put in?
It will depend on what the question asks you for as to which ones you're trying to cancel out. Okay, so we'll see. Have a look at this first example here. So you can see already I'm not using x's and y's. It says find dv over dt, given that dv over dr equals 5r and dr over dt equals 2. So the one that I'm trying to find is dv over dt. Now starting with that top variable, the v, I'm going to put dv on the top. What is my third parameter that hasn't been used here yet? The r. So let's put dv over dr. Knowing that I'm going to need to cross cancel, it's going to be dr over dt. Now, do I have all of those things?
Yes.
dv over dr was 5r, and dr over dt was 2, so that just makes 10r. Easy enough, right?
Yeah.
They're going to get a little bit harder, unfortunately. Let's try B. Find dn over dt. So that's the one I want. dn over dt. Okay, even before I look at the other stuff that's given to me there, what is my chain rule going to be?
dn
Yep, I'm going to start with a dn.
over dp.
My third variable is the dp. Good. Which means I'm going to need a dp on the top of the next one over
dt.
dt. Is everyone following that?
We're going to be
Yeah? So, okay, the dn has to be there and the dd has to be there because that's what I want for my final answer, the dn over dt. And the dp is the third variable that is going to be cancelling out. Okay, so let's have a look at what we've been given now. I've been given dp over dn. So dp over dn is not quite what I want. I want dn over dp. So if that's equal to 4n, correct, I do the reciprocal of both sides, turn the dn over dp upside down, and the 4n, what's the reciprocal of 4n? 1 over 4n, all of it on the bottom. Do I know dp over dt? Yes, that was given in the question, so we can sub in. dn over dp was 1 over 4n times dp over dt is 6. So timesing that together, I would get 6 over 4n, which of course would simplify to be 3 over 2n. Okay, so those couple of questions, just practicing getting those rates. But let's keep going. Question 2. If a is equal to h squared minus 5h, did I say h? If a is equal to h squared minus 5h, and h is equal to 3t squared, okay, I'm given a couple of equations there. Find dA over dt. Well, I've got two equations to work with, so I'm going to need to differentiate them. Let's see what I get when I differentiate. From this first one, it's in an A equals equation, right? So it's going to be derivative of A with respect to, what am I differentiating?
Oh, D is for derivative.
D is for derivative, the H, that's right, the H is the variable, so it's going to be a dA over dH. Okay, so I'm differentiating that just like the H would be an X in our other types of equations. So you bring the 2 down the front and it becomes 2H minus 5. Yeah? All right, take the second equation. What is my first letter? I'm differentiating H. Good. So differentiating H with respect to the T, because my variable in there is a T. So what is my derivative going to equal? Yep, 6T.
That's the second.
No, not even the second derivative. Oh, you've got to sub in the T. Don't sub in the T yet.
Oh.
Don't save that to the end. I was wondering what you're talking about for a second. I understand. Don't sub that in yet. Okay. We are trying to find the dA over dt. All right. This is what I want. dA over dt. Okay. So I'm going to need, in my fractions, I'm going to need a dA here and a dt there. What's my other variable? The h. So it's going to be dA over dh times by dh over dt. Oh, look, that's exactly what I have. I don't even need any reciprocals. So we can sub those in. dA over dh is 2h take away 5. And dh over dt is 6t. Because we're multiplying that, we do need to put this in brackets because it has to all be multiplied by that 6t. So I'm just going to put the 6t first because we're used to seeing brackets come second when we write an expression like this down. Okay, once we have found the rate that we want, the dA over dt, only at the end can you substitute in any values that you've been given. So I was told that t is equal to 2, so I can sub that in. But you can expand it if you want to, but you don't need to. So I'm just going to write down now when t equals 2, my dA over dt equals, unfortunately I still have a h in there. We don't know what h is, but we do get 6 times 2 bracket 2h minus 5, which is going to be 12. 2h minus 5. Okay, so you could expand it. Yes, that's fine. It'll be the same thing.
24h minus 6.
Yes, that's fine. Okay, everyone's still doing okay? Wonderful. Okay, because what's going to happen is these questions are going to get a little bit more in the application side of things. You want to be able to be given a situation over here, and so in this question's been very nice to us. It's given us a diagram. We have to find the equations and then obviously be able to find the different rates that we want to get from it. So there's actually a few parts to this question.
I just want to check something. Wait, if it goes, oh, okay, never mind, it's fine. I just read something
There's
wrong.
so many questions.
Okay, so question 3, there's a part, this first bit, I think I got this question out of the textbook. This is not even part A, it's just building the equations. There's a part A and a part B over the page from this. So the first thing we want to do is show that if we take an equilateral triangle, which you've got the diagram there, of side length S, that we get an area of 1/4 s squared root 3 and a height of 1/2 s root 3. Now, the diagram has been very helpful to us because it's told us that we need to put a perpendicular height in there, which means it's going to split the bottom side of that equilateral triangle into 1/2 s and 1/2 s, right? So it divides that bottom side in half. Okay, so although it does say the area formula there first, the formula for the area of a triangle is 1/2 base times height, correct? Yeah. And I would need to know the h.
Oh, so the height would be...
So it's actually better if we start by finding the h first, because we're going to need that for the area equation. Okay, so the h. Now this equation that I'm trying to get over here is an equation of h only in terms of s. So over here in my triangle, I've only got h's and s's. What could I use to relate those two variables? Pythagoras.
Yes.
Pythagoras, you said it, Isaac, good job. Pythagoras' theorem. If I take just one of those triangles, let's look at this triangle here. Pythagoras' theorem says that the hypotenuse squared is equal to the two shorter sides added together, correct? That's our Pythagoras' theorem. But I have got s squared for my hypotenuse is equal to shorter side h squared, and my other shorter side is a half s all squared. And I put that in brackets because you have to remember to square that half as well. So if I do that, I'm going to get s squared equals h squared plus, squaring the half, I get a quarter s squared. Now remember, I'm trying to get h by itself and the s on the other side. So let's get the h squared over here on the left. And I'm going to move the quarter s squared across to the other side. So it'd be s squared minus a quarter s squared. They are like terms. They're both s squareds. I have one s squared minus a quarter s squared, which is what? 3/4, correct. 3/4 s squared. We're almost there. If I just want h, what do I need to do? I have to square root that whole thing. 3s squared over 4. Now, if I look at everything underneath that square root sign, can I square root the s squared? Can I square root the 4? The only thing I can't square root is the 3. So I leave that part in surd form. I have square root of 3. I can square root the s squared to be a normal s, and square root the 4 becomes 2. Now it's written a little bit differently, but you can see that that is actually the same as what's highlighted up there in yellow. Let's just write it the same because that's the way they want it. So h is equal to, just bringing the half out the front. Then they've put the s next, and then the root 3 last, which is a little bit odd because we don't normally like to have the letter in the middle, but that's how they wrote it. Okay? All right, we have the h. That's equation number 1 done. We also, remember, need to find the area now, the pink one that I've just highlighted.
We do that because we have to show.
Yeah, because I have to show those are the equations.
Yeah.
The area of a triangle, if it's a right angle triangle, is always half BH. What's the base of the whole triangle? Forget the orange one now, the whole big equilateral triangle, S. What is the height of that right angle, that whole triangle? Yes, the H, but I don't want to put H in there. I've just found, yes, I have just found that it is half S root 3. Okay, let's just tidy it up. S times S is going to make S squared. I have a root 3 there as well, which I'll put out the front. And 2 times 2 is 4 for the bottom, which is the same thing. Again, they've just written it out the front. And put it in a weird order. The 2's on the bottom there. So the half times the half makes a quarter, or a 4 on the bottom. Okay, so we have our 2 equations. We need these 2 equations now to do part A and B on the next page. So part A, believe it or not, we're only just really starting the rates part of the question. Find the formula for the rates of change of area and height in terms of the rate of change of the side length. It's not going to be just a nice number answer here. They're going to be expressions in terms of rates. Okay, so the first one I want is the rate of change of the area in terms of time. So that's going to be a dA over dt. Rate of change of the area and the rate of change of the height has to be in terms of what's happening over time, because yeah,
rate of change, it can't change in no time.
That's right. So it's how it's changing over time. Let's keep going. Yes. It's going to be a dH over dt is the other one that I want. So it's both of the 2 equations. I had an A equals and a H equals, right? They were my 2 equations up there. And I want to find those as they're changing over time is what it's asking for. So starting with the dA over dt using the chain rule, it's going to be a dA over something times a something over dt, because I know I need the dA over dt. What do you think those other diagonal ones they're going to be?
S.
Yes, why?
Because it's the one that you're...
Look at my equation up here for A, it's in terms of S, isn't it? So that's my other variable in there. So ds and ds. All right, I can't quite sub into that rate yet because I need to know what those derivatives are. So the dA over ds, looking up here, so I've kind of kept this at the top of the screen here, my A equation, I need to differentiate that. So it's going to be dA over ds equals, okay, it's the s squared there that we're differentiating. The 2 needs to come down with the quarter, which will make a half. So a half, I really don't like the root 3 at the end. I'm going to put the root 3 on the top over there. Root 3 over 2s.
Does it not?
It doesn't really matter. But I like to have my numbers together. It's kind of weird having that root 3 on the end and my letter in the middle. I did it because that's what the question said. But all right, so there it is. So now I can find, I'm going to use this rate of change formula. I'm going to sub into it. The dA over dt is going to be dA over ds, which is root 3 over 2s times by ds over dt. And that's all we can do for now. It does say in there, find the rate of change in terms of, wait, let me read it again. Find the rate of change of the area and height in terms of the rate of change of the side length. This thing here is the rate of change of the side length. So I've got it in terms of that. At the moment, I don't know what that is, so it just has to stay in there. In part B, we work out what that is. Okay, so now let's find a similar equation for our dH over dt. What is our chain rule going to be? We know there's going to be a dH there. Yeah, and there's going to be a dt there. So in the H equation, it's also S as our other variable, so ds's in there. So using our H formula, we want to differentiate the S. It's just an S to the power of 1. So it's just going to be the root 3 over 2, correct. So dH over ds equals the half times the root 3, or root 3 over 2. So then you're putting that into that chain rule, dH over dt equals dH over ds, which is root 3 over 2, times by the ds over dt. Again, that's in terms of my rate of change of my side length. Both of those equations have a ds over dt in them. Okay?
Why does it just equal root 3 over 2?
Because I'm looking up here at my derivative, at this equation here, and s is my only pronumeral. It's like having an x. When you differentiate the x, it's only the numbers that remain. So the s will disappear, and I just have the half and the root 3 when you differentiate it.
Oh, because it's a square on that side.
Yeah, the other one had a square, which is why, yes, that one changed. Okay, on to the last part. It is.
It's just to the half.
Oh, okay, sorry. Oh, you'll have to write yours neater.
Rates of change, is that what gives us the dt?
Yes. Whenever it says rates, you know it's going to be talking about a derivative of some kind.
What? Like no rate time? How did we get the dt?
Because change can't get on that time period.
Yeah. Yeah. And the other clue is, and I guess we haven't read this far ahead, B kind of confirms it here. Because when we look at this one, it says, hence find the rate of change. Hence find the rate of change in which the area and height are increasing when the side length is 12 centimeters and is increasing at 3 millimeters per, what's that S? Seconds. So it's confirming that is a time that our rates are in terms of. So that's a unit that we're needing to use right there. So often looking at the units when you're given something like that will tell you what your variable is going to be in there. Okay, so we are given some information in here which is going to help us with these expressions we've got. So we know, first of all, that S, because S was the side length, it says that the side length was equal to 12 centimeters. And it says that the side length is increasing at a rate of. When it says that, the side length is increasing at a rate of, so I know that's the ds over dt, 3 millimeters per second. And it's always good to check. The side length can be measured in millimeters, yep, and time can be measured in seconds. My derivative matches the units that I've been given. Can you see a problem?
Absolutely not.
Can't you? Look back to S.
Yeah, the 3 millimeters doesn't.
Yes, if I've got a rate of 3 millimeters, I can't have a side length. I'm not going to be able to use 12 centimeters.
20 millimeters.
I'm going to have to make sure that's in millimeters as well. So let's just quickly change that. 120 millimeters. Okay, you always need to make sure your units are always consistent. Okay, so if I want to find, back up the top here, if I want to find the dA over dt, back up to that first chain rule that I found.
Where's that from?
Right here, that one. dA over dt. There? Do you want me to highlight it again?
Why are we finding that?
Find the rate at which the area and the height are increasing. So it's back to those rates of change of my area and my height, which is those expressions that I found. So I'm just going to be subbing into those formulas, the new information that I've been given. So the root, I have root 3 over 2 s, but what's s?
120.
Yeah. Times ds over dt, but what's that? 3. Okay, so 120 times 3, that's 360, divided by 2 is 180 root 3. Don't go to decimal if that's what you were doing. Just leave it in third form, please. What would the units, you know how we had millimeters per second there? What would be the units for this one? It's a dA over dt. Come on, physics people. Area is millimeters squared and time is seconds.
Millimeters per second per second.
Millimeters per, no, we're not doing the time twice. This time is just one.
Oh yeah, true. We're not
Okay.
accelerating.
Okay. Yes, does that make sense? Okay, let's do the other one. The dH over dt, using my second equation, was root 3 over 2 times by ds over dt, which is 3, just the 3. Nothing else to sub in. So that's just 3 root 3 over 2. Can't even simplify it. What are my units going to be? Height is measured in millimeters and time is seconds, so millimeters per second. Yeah? Not bad, eh? All right, I like this question. This is our last one.
Just look how many questions there are.
This is the last one.
No, look at the homework.
Oh,
No,
yes.
boy.
Calm down.
Maths teachers love workshops.
I'm still
They're
working my way
always,
through it.
you know.
I'm just going to do the test next time.
Okay, you ready? The water trough in the diagram is in the shape of an isosceles right triangular prism, 3 meters long. A jackaroo is filling the trough with a hose at a rate of 2 liters per second.
Why is the jackaroo there?
I don't know. I did not make this up.
I don't know.
Okay.
Animals when you're killing its own water trough.
Yeah.
Animals can use hoses.
Not now. So we have a diagram there of our water trough. Gentlemen, concentrate, please. We have a diagram there of our water trough. We want to first of all show that the volume of the water in the trough when the depth is h centimeters is going to be given by V equals 300 h squared centimeters cubed. We're trying to find the equation of the volume of that water trough when it's filled h high, whatever h is. So it might only have a little bit of water in the bottom. H might be a small amount, or it could be filled all the way to the top. That's why h is the variable, right? Depending on what the height it is filled to. So first thing we need to do, if I'm trying to find a volume, it's a triangular prism. So I know I need to find the area of the triangle on the front times the height. The height part is easy. Not a third, it's not a pyramid, it's a prism. We have the 3 meters here. That's the height going back from the triangular face. There is a little concern that you need to be careful of right from the very start.
2 H's.
Not yet.
Centimeters.
See this? Centimeters cubed. And the measurement I've been given is in meters. So I need to put in 300 centimeters. Don't use the meters. Okay? The other thing, we need to find the area of that triangle on the front. To find the area of a triangle, you need to know the half the base times the height. Now, the height that we're going to use, we're given the letter H. And we know it's a right angle. If we're splitting it down the center there like that, it's an isosceles triangle, we're told, which means that this here and that there are the same. And we're also told there's another right angle in that diagram. I didn't draw it very well. Mine doesn't look like a right angle, but that's a right angle there. If I look at the big isosceles triangle around the outside, what are these two angles here going to be?
The same.
Which is what, how many degrees?
4,
45, correct. Because of that right angle, because of this right angle down here, those other two angles there must be 90 together or 45 each. Okay, so I know that this is 45 and I know that this is 45.
Wait, how do you know that's 90 degrees?
It's in the diagram up there on your water trough, see?
Oh.
Okay, then he's going to blow your mind even further. Now look at just one of those little triangles. I'll trace over in orange. I'm going to look at this triangle here. Remember, my diagram is not to scale. It's definitely not to scale. If I have a right angle here, and this is 45 degrees in the corner, what's this one down here? It's 45 as well.
And then it makes 90.
Okay, so all of these angles in here are 45 degrees. So, if it is H, see my H, the height of that triangle going down, if these two angles are 45, it's going to be H there as well. And it's an isosceles triangle, it's going to be H here as well. Which means the whole way across is 2H.
Pythagoras Theorem.
Not even Pythagoras Theorem, just using isosceles triangles.
Yes, I was just going to do H over tan 45, which then would just be an H over 1.
Okay. H over 1.
But then there's
All right.
4 of them.
Yeah.
Yeah.
So 2H.
That's right, that works too.
Why
Oh my
is there
goodness,
H's
baby, this is
here?
smart.
Sorry?
Why did you put H in again?
Sorry?
Where did you get the H from?
It was given in the question right here.
No,
H.
no, the other ones.
Isosceles triangle. If these are 45 degrees, then that is 40. The base angles are the same, which means the sides opposite are also going to be the same. So they're both going to be H.
Just the
So this is like an equilateral triangle.
The outside one is equilateral. Actually, no, it doesn't say it's equilateral, but it totally is going to be. But it didn't tell us that. But it does turn out it is.
How's it equilateral? Because it's only got 45 degrees, not 60.
Oh no, yeah, that's not. It's not. It's still not equilateral. It's only isosceles.
It's an isosceles.
We don't need to know those other. We don't need to know those other two sloping ones.
The bed this morning's clicked on.
He has. He's on fire today.
I had an extra coffee this morning.
That's
60 degrees.
All right, let's not get stuck down. Let's keep going. I want to find the volume, remember. We've found all these details about this triangle. To find the area of that triangle on the front, we need the half the base times the height of the triangle. And then I need to times by the 300 going back, which is the height of the prism. Using my triangle, my base is the 2H that I found, and the height is the H going down, times by the 300. Half times 2 is just 1, so it's just going to be 300 for the numbers, and H times H makes H squared, and we do know that that is in centimeters cubed because we made sure that we put centimeters in there for that length of the prism. Okay, so we've done part A. That's all building the equation, and sometimes that can be the trickiest part. How do we build these equations that they're wanting us to use? Then we get to part B, which is where the rates come in. Given that 1 litre is equal to 1,000 centimetres cubed. Now, why on earth is it giving me that? Do you remember back here, it said that the trough was being filled at 2 litres per second. That is a rate, isn't it? If I'm filling something at 2 litres per second, litres is what kind of measurement?
Volume.
It's a volume, it's a capacity. But I can call that a dV over dt. It's how the volume of the water is changing over time. At the moment, we've been told that it is 2 litres per second. We don't want to work in litres though, because our volume formula is in centimetres cubed, which is why it gave me this little conversion. 1 litre is 1,000 centimetres cubed. So instead of saying 2 litres per second, I can change it to 2,000 centimetres cubed per second. Okay? I also am told in the question, it says, given that 1 litre is 1,000 centimetres cubed, find the rate at which the depth of the water is changing. That means, what am I trying to find there? The rate at which the depth of the water is changing. What's the depth? What letter? So that's the dH over dt. So the rate at which the depth is changing when h is equal to 20. So there's another variable that I've been given. 20 centimetres. So first of all, using our chain rule, dH over dt, I'm going to need a dH over something times a something over dt. What is my other variable?
dV.
V, correct. Because I've got a volume equation up there, don't I? So it's going to be over dV and then dV over dt. The dV over dt part, I've already got that. That's going to be easy. It's the dH over dV. That's a little bit more work. I have an equation for V in terms of H. So taking my equation that I found up here in part A, just over on the side, V is equal to 300H squared. I can differentiate that, which is dV over dH, times the 2 down the front, becomes 600H. But I don't want dV over dH, I want dH over dV, so I take the reciprocal of both sides, 1 over 600H. Now I have everything I need to sub into my rate there, rate of change. So then the dH over dV is the one I just found, the 1 over 600H, times dV over dt was 2,000. And that's going to equal 2,000 over 600. And when you've gotten this far, you can now substitute in the H. What's H equal to? 20. And then you can type that all in, and you will come down to be 1/6. What's the units? It's a dH over dt. H is measured in centimetres and T is measured in seconds. So centimetres per second. Don't sub in any variables like the H equals 20 there until the very end. Sometimes I get people that sub things in before they've differentiated, which causes you huge amounts of problems because then you have nothing to differentiate if you've already subbed in your value of H. Okay, you only sub things in at the very, very end. All right, that's it for 16A.